You know, deep learning, it feels like it just exploded onto the scene, right? Like it appeared out of thin air and completely changed our world in just a few years. But the real story, oh, it's anything but sudden. It's this incredible, decades-long drama of massive hype, followed by crushing disappointment, and then this tiny group of believers, people who kept an idea alive when pretty much everyone else was calling it heresy. Okay, let's get into it. And that brings us to this central idea for our whole story, a research tsunami. That's what Stanford's Christopher Manning called it. By 2015, deep learning was just washing over everything in AI, replacing all the old methods with this unbelievable speed. So the question is, how did this massive wave build up for so long, basically unseen? To figure that out, we've got to go way, way back, to the very beginning. Okay, so let's set the scene. We're in the 1950s, and the optimism is just off the charts. Researchers were totally fascinated by the most powerful computer they knew of, the human brain. And the dream, the big dream, was to build a machine that could learn, not from being programmed line by line, but from experience, just like us. And this was their first real shot at it. It was called the Perceptron. Frank Rosenblatt cooked this up in 1958, and it was such a simple, beautiful idea. Basically, it's a super simplified model of a single neuron. It takes in some data, decides how important each piece is, those are the weights, and then makes a decision. Do I fire or not? A 1 or a 0? But here's the magic part. It could learn. It could actually adjust its own weights depending on whether it got the answer right or wrong. So, the hype, oh man, the hype was, well, you can just see for yourself. This quote from the New York Times is just wow. They're not talking about a better calculator. They're talking about an electronic computer that will walk, talk, see, write, reproduce itself, and be conscious of its existence. I mean, come on. They were promising a conscious, self-replicating being that would go explore other planets. The expectations were set impossibly, astronomically high. But well, reality has a way of crashing the party, right? The Perceptron had a killer flaw, a very clear mathematical limit. See, it was great at solving problems where you could draw one single straight line to separate the yes answers from the no answers. But it completely choked on problems that weren't linearly separable. And the most famous example is this simple logic puzzle called XOR. It was a mathematical dead end. It just couldn't do it. And then, in 1969, two big names in AI, Marvin Minsky and Seymour Papert, they published a book that just ruthlessly laid this weakness bare for everyone to see. And their analysis was devastating. It basically convinced the entire research world that this whole neural network thing was a total dead end. So the funding just vanished, projects got scrapped, and the first big AI winter set in. So for years, neural nets were just out in the cold. But a few people, a very few, they knew the problem wasn't the idea of a network itself. It was the fact that they only had a single layer. The real puzzle, the big challenge, was figuring out how in the world do you train a network that has multiple, hidden layers inside. And that was the million-dollar question. I mean, think about it. If your network spits out the wrong answer, you know the final layer messed up. Easy enough. But how do you assign the blame? How do you know which of the hidden neurons in the middle are the culprits? Which of their weights do you need to tweak? It's called the credit assignment problem, and it had everybody completely stumped. The solution, which really took off in 1986, was this incredibly elegant idea called backpropagation. And it's kind of cool. Instead of going forwards through the network, you start at the very end. You figure out how wrong the final answer was. That's your error. Then you work backwards, propagating a little piece of the blame back to each neuron in the layer before it. And you keep doing that all the way to the beginning. The key thing is that every single weight in the entire network gets a tiny little nudge in the right direction. It allows the whole system as one to learn. And just like that, the AI winters started to thaw. Backpropagation actually worked. This breakthrough meant researchers like Yann LeCun could finally build these multi-layered networks that could solve really complex real-world problems. By 1989, his system was reading handwritten zip codes for the U.S. Postal Service. It really seemed like the revolution was finally here. But it wasn't. In this kind of cruel twist of fate, just when neural nets were making a real comeback, the rest of the world just moved on again. A second, even longer AI winter started to set in, and the few people who kept the faith, well, they had to band together in what they later joked was a kind of conspiracy. So what went wrong this time? Well, it was basically three things. First, backpropagation had its own kryptonite. When you made the networks really, really deep, we're talking lots of layers, that error signal you're sending backwards, it would just shrink and shrink with each step until, poof, it vanished. It was called the vanishing gradient problem. Second, these new shiny methods like support vector machines came along. They were mathematically elegant, they were more reliable, and frankly, they often just worked better. And that led to the third thing. The culture changed. Neural nets started to be seen as messy, kind of a black box, old-fashioned. They literally became heresy in the machine learning community. So through these dark ages, we're talking the 90s and the early 2000s, almost everyone gave up. But there was this tiny group of researchers who just refused to quit. Geoffrey Hinton, Yoshua Bengio, and Yann LeCun, who we now call the godfathers of AI. They just kept plugging away. And they were kept afloat by this super important grant from Canada's Institute for Advanced Research, or CIFAR. It was a lifeline when basically no one else would fund them. And they had a plan. It was slow and methodical. In 2004, Hinton gets CIFAR to fund this new program. By 2006, his lab has a massive breakthrough, publishing a paper showing that it was possible to train deep networks. You just had to be really clever about how you started the weights, kind of pre-training them layer by layer. And to get away from all the bad juju around the term neural nets, they gave their field a new name, deep learning. The conspiracy was officially on. All right, this brings us to the final act. This is where it all comes together. The theoretical ideas were there, simmering. But it took a perfect storm, three different forces all hitting at the exact same time to finally unleash that tsunami. So the big question is, why now? Why did it finally work this time when it had failed before? Well, Geoffrey Hinton himself boils it down to four main things. Number one, data. We finally had massive labeled data sets like ImageNet. Think millions of images. Number two, compute. Our computers, especially the GPUs made for video games, were millions of times faster. And finally, all those little algorithmic tricks they'd been working on during the AI winter, like smarter ways to initialize the weights and a much better, simpler on-off switch for neurons called ReLU, they were all ready to go. So here's the key takeaway, the magic formula, if you will. Deep learning wasn't just one single breakthrough. It was the perfect convergence of these three things all at once. Tons of training data, plus massive parallel computation, plus these new scalable, smart algorithms. You needed all three. Take one away, and the whole thing doesn't work. And this was the moment the world had no choice but to listen. It was the 2012 ImageNet competition, the Olympics of computer vision. Hinton's team shows up with a deep convolutional neural network, and it didn't just win. It absolutely demolished the competition. Look at that error rate, 15.3%. The runner-up was way back at 26.2%. That's not just winning, that's a statement. It was a total mic drop moment for the entire field. And that was it. That was the moment. The tsunami had finally hit the shore. This idea that was born in the 50s, declared dead in the 60s, brought back to life in the 80s, and then scorned as heresy in the 90s, had finally, undeniably proven its power. The heretics were now running the show. The revolution that came after that has pretty much defined the last decade of tech. But let's be real, deep learning isn't magic, and it has some serious limitations. It's incredibly data hungry, it can be fragile, and it's often a complete black box. We don't always know why it works. And that leaves us with the big question for today, right? What comes next? What's the next incredible chapter in this story going to look like? What's the next wave that's building right now just out of our sight?